Even though it's 93 million miles away, the sun is capable of producing temperatures in excess of 130 degrees Fahrenheit here on Earth. It provides the heat needed to support life and to continue many natural cycles. We get the sun's heat by a process called radiation. That's just one way that heat energy can move from one place to another. Here at the plant, we use two processes to transfer heat in heat exchangers: conduction and convection. Using a heat exchanger like this one makes our operations more energy efficient. During this program, we'll discuss two topics: heat transfer, specifically conduction and convection, and heat exchangers, the factors affecting their efficiency, design, use, and maintenance. As you know, warm materials tend to lose heat to cooler ones. When the materials are in direct contact with one another, the process of heat transfer is called conduction. Another way to transfer heat is by convection. This is caused by a change in fluid density that sets up currents. The following example will illustrate both processes. If a metal container of hot water is touching another filled with cold water, the temperatures of both will change because of heat transfer. The greater the temperature difference, the faster the transfer takes place. In this example, the heat is carried through the metal walls by conduction. The cold water closest to the wall absorbs the heat directly from the metal and increases in temperature. This warm, less dense water rises and is replaced by cooler water. Then, a convection current transfers heat to all parts of the water. This transfer results in a change in temperature for both containers. Conduction and convection take place almost simultaneously to move heat from one fluid to another. In conduction, an important factor affecting the rate of heat transfer is the type of conductor used. Conductors vary widely in their ability to transfer heat. As you may expect, metals are better conductors than glass or wood materials. Let's see how conduction and convection work together in a simplified heat exchanger. Because of the difference in temperatures, the heat from hot oil inside the tube is conducted through the tube wall to the cooler liquid in the shell. The hot oil becomes cooler while the cool water absorbs heat. In this heat exchanger, the fluids are being pumped through the vessel. This causes turbulence, a disturbance in flow. Turbulence results in a faster, more efficient flow of energy. Velocity also influences the rate at which heat moves between two fluids of different temperatures. Water that travels too quickly can't absorb enough heat. The optimum velocity represents the most efficient heat transfer. Another consideration for efficiency is the area of contact. The greater the surface area, the more heat will be transferred. To ensure a large surface area, most heat exchangers have a system of tubes inside. The liquid in these tubes is referred to as tube side flow. Another liquid is directed through the space around the tubes. This is called the shell side flow. By having many tubes, more heat can be transferred. So far, we've discussed conduction, heat transfer by direct contact, convection, heat transfer by current movement, and several factors that influence the efficiency of heat exchangers, including temperature difference, conducting material, fluid turbulence, fluid velocity, and surface area. In addition to these, another factor that affects efficiency is the direction of flow. You'll learn about this factor in the workbook. Stop the tape and turn to workbook period 1. Be sure to complete all of the self-teaching frames as directed. In this section of the program, you will learn about heat exchanger design, including flow arrangements. Because tube heat exchangers are the most prevalent, the program addresses problems that arise when using tube heat exchangers and solutions to these problems. There are several designs for heat exchangers. In addition, these designs are varied as necessary depending upon the characteristics of the process fluid. In general, there are plate and tube heat exchangers. Each transfers heat from one fluid to another. This is a plate heat exchanger. Note its form and size. As its name implies, it's made of corrugated plates. The plates are held together with an external pressure plate that can be moved for maintenance and cleaning. Internally, fluids enter each plate compartment. The flow is set up so that the plates with hot liquid alternate with those containing cooler liquids. Large surface areas and the natural turbulence caused by the corrugated metal plates allow for efficient heat transfer. Plate heat exchangers may be used because of the specific demands put on the system by the characteristics of the process chemicals. For example, for a highly corrosive chemical that must be cooled, a titanium plate heat exchanger may be best. Another type of heat exchanger, and the most common, is the tube heat exchanger. Its design consists of a set of metal tubes carrying one fluid and the space around those tubes, known as the shell, carrying another fluid. As we'll see, the internal arrangement of the tube heat exchanger is critical for efficient heat transfer. To increase the amount of heat transfer, the tube side fluid can be put through the exchanger more than once. To do this, a channel baffle is built into the head of the exchanger. This baffle or partition directs the flow through half of the tubes in one direction and through the other half in the opposite direction. Here is a channel head baffle that directs the tube side fluid through the exchanger 2 times. Every time the hot fluid makes a pass through one channel, it gives up more heat. Increasing the number of tube side passes improves the efficiency of an exchanger. The shell side flow can also be changed to produce high efficiency. As these longitudinal baffles force the shell side fluid to flow back and forth over the tube bundle with each pass, shell side fluid absorbs more heat. Another arrangement involves segmental baffles. They can be cut vertically or horizontally and are positioned to face in alternate directions. These baffles will allow the fluid to flow across the tubes a number of times and keep the fluid turbulent. The more turbulence, the more energy is transferred. Segmental baffles can direct the flow to be horizontal or vertical depending upon the fluid being used. If the liquid is dirty, the sediment will often build up behind a horizontal baffle. This decreases efficiency by blocking the flow. If the force of the fluid entering the shell is too great, impingement baffles may be used. These baffles direct flow to the sides of the exchanger, which reduces internal erosion. In addition, the fluid contacts more surface area and increases efficiency. Despite careful design considerations, there are some problems that occur whenever 2 fluids with different temperatures run through the same piece of equipment. This is because metal expands and contracts in length because of changes in the temperature. Even under normal operating conditions, this natural process will stress certain parts of the exchanger. In a fixed tube sheet exchanger, the tubes and tube sheets are permanently attached or fixed to the shell of the exchanger. Whenever these parts expand and contract, the tube joints undergo stress. Eventually, this stress may cause leaks to develop at the tube joints. There are basically 3 designs that deal with the possibility of leakage. Some fixed tube sheet exchangers, the tube bundle is anchored between double tube sheets. If a leak does occur, the fluid flows into the space between the tube sheets and can be safely drained from the exchanger. This design may lessen the effect of a leak, but it cannot lessen the stress that thermal expansion puts on the tubes. A fixed tube sheet exchanger can only be used where the temperature difference between the 2 fluids is small. The next example is a tube bundle from a U-tube exchanger. In this type, the tubes are free to expand because they're only attached at one end of the tube sheet. So a U-tube exchanger can handle fluids that vary greatly in temperature. Although the U-tube bundle can be removed from the shell, the bends in the tubes hinder internal inspection and cleaning. A third type of exchanger is designed to allow both thermal expansion and easy maintenance. Because only one tube sheet is fixed while the other floats horizontally, this is called a floating head exchanger. The tubes are free to expand and contract in response to the temperature changes without stressing the joints. And the bundle and floating head can be removed for cleaning and inspection when necessary. This cutaway view of a floating head exchanger shows you one disadvantage of its design. There is a clearance space between the shell and tubes. It's needed so that the bundle can be removed for maintenance. The shell side liquid will tend to flow through this space, an area that offers little resistance. When this happens, efficiency decreases because the shell side fluid does not come into contact with enough tube surface. We've covered a lot of material in this section dealing with the internal flow arrangements and problems that may occur. To summarize, there are several types of baffles that affect flow: channel head, longitudinal, segmental, and impingement. Expansion and contraction cause stress. This can be managed in several ways: with the double tube sheet to collect leaks, with a U-tube exchanger to allow for expansion, and the floating head exchanger, which makes cleaning and inspection easy. To review this information and to learn more about heat exchanger design, stop the tape and turn to Workbook Period 2. In discussing heat exchangers thus far, we've examined factors that affect their efficiency, and we've looked at design issues. In this final segment, we'll cover specific applications and general maintenance. The heat exchangers we've seen up to now have all been used to heat a process liquid. In some instances, however, the purpose of heat exchange is to remove heat from a fluid that requires cooling. Suppose we wanted to convert steam generated by one process into feed water for another process. To do this, a shell and tube exchanger can be used as a condenser. This cutaway will show how the condenser works. Water enters the space between the head of the shell and the adjacent tube sheet and flows through the tubes to the opposite end. Steam enters at the top of the shell and flows down and between the condenser's tubes. When the steam is cooled, it condenses to water and falls into the hot well at the bottom of the condenser. Air also may be used to cool steam. Here, a fan blows air across tubes that carry steam. Although not as efficient as water, the air absorbs heat from the steam and the steam condenses. An air-cooled system may be used if water is scarce. Another application for heat exchangers is as a reboiler. Reboilers are used in systems that heat and vaporize hydrocarbons. This one is a kettle-type reboiler. It is simply a shell and tube exchanger surrounded by an enlarged shell that accommodates vapor. Let's examine the system. This system includes a distillation tower, a furnace, and a kettle-type reboiler. The furnace heats oil, which is pumped through the tubes of the reboiler. Meanwhile, liquid isobutane flows from the bottom of the distillation column into the shell of the reboiler. The heat from the oil is transferred through the tube walls and vaporizes some of the isobutane. The isobutane vapors are then channeled into the distillation column. These vapors provide the heat needed for distillation to take place. The isobutane vapors lose heat, condense, and fall to the bottom of the tower, starting the cycle again. Coolers are heat exchangers too. As the name implies, coolers lower the temperature of the liquid or vapor. In the next example, kerosene is being cooled before going to storage. Cooling water passes through the exchanger twice, while the kerosene makes only a single pass. As the kerosene moves through the exchanger, it releases some of its heat to the water. The baffles keep the flow of the kerosene turbulent, ensuring maximum contact between the kerosene and the tubes. With this contact ensured, the kerosene is cooled efficiently and can then be stored safely. The final application that we'll look at is one that converts waste heat into valuable steam. The heat exchanger used for this purpose is called a waste heat reboiler. Let's look at a diagram of a typical waste heat system. The main components are a steam drum, a waste heat boiler, and a distillation column. Water from the steam drum is sent through the tubes of the waste heat boiler, while hot oil from the bottom of the distillation column moves through the shell. As water absorbs heat from the oil, part of it is vaporized and turns to steam. The steam carries small droplets of water through the boiler. This mixture of steam and water droplets flows up into the steam drum. Here, the two fluids are separated from one another. The steam is sent to the plant steam system, while the water is channeled back to the boiler. As you know, all the equipment involved in these applications requires periodic maintenance. For this reason, we'll now discuss some basic operating problems and how to handle them. Fouling is a common and destructive enemy of heat exchange. A low-velocity flow can start the buildup of deposits on internal surfaces. These deposits can cause changes in temperature and pressure. The deposits have several sources. Process fluids may contain solid sediments. Once they settle, a restriction to the flow develops, and the restriction then causes more settling. Corrosion is produced when the metal of the exchanger interacts chemically with the process stream. These deposits can break free eventually and foul the exchanger tubes. The warm exchanger provides a comfortable environment for the growth of certain organisms. The tube surfaces may become contaminated with algae. There are several ways to control fouling in a heat exchanger. One way is to add dispersants. These will prevent insoluble materials like dirt from forming solid deposits. Another control method is to add chemical inhibitors that will keep chemical reactions from taking place. Or anti-foulants can be added to the process streams. These chemicals prevent biological growth. After fouling has occurred, removal methods depend on the type and severity of the deposits. Deposits on the outside of tubes can often be removed by hydroblasting, a high-pressure stream of water that loosens and washes away the deposits. Streams of water or steam can also move the deposits from the inside of a tube. If water and steam fail, chemical cleaning may dissolve the deposits. If, however, the deposits resist both chemical cleaning and hydroblasting, the exchanger must be completely dismantled and the deposits scraped off. At this point, it may be best to retube the exchanger. As always, during shutdown and startup, workers must follow safety precautions. Nitrogen and other inert gases are used to purge the exchanger of hydrocarbons and air. These gases can get trapped inside the exchanger where they interfere with the heat transfer process. These gases can be released by venting according to the procedure specific to your unit. Condensers are susceptible to problems caused by other gases as well. One problem occurs when air leaks restrict the flow of water by causing vapor binding. To eliminate vapor binding, open the vent in the water exit line. Another problem is a reduction in cooling capacity. This can occur when non-condensable gases are present in the process side of the condenser. You can correct this type of problem by venting the process side of the condenser to release the trapped vapors. Leaks are another important maintenance concern. Whenever exchangers are down for cleaning, they're almost always tested for leaks. But before dismantling the exchanger, there are some preliminary tests you can perform. One simple way to test for leakage is to take a sample of the lower pressure fluid and check it for contamination. If the fluids are very different in appearance, like oil and water, just looking at the sample should tell you if there's a leak. This sample, for example, has a small amount of oil in the water line, a sure sign of a leak. However, if the fluids are very similar in appearance, chemical testing may be needed to detect the results of a leak. This must be done in the lab. If neither the visual nor the chemical tests are conclusive, a test using high-pressure water may be done. This is called hydrostatic testing. Before it can be done, the exchanger must be taken offline and drained. If you're checking for tube side leakage, the tubes are filled with water under pressure. If the tubes or joints are leaking, the water will be forced through the leak points into the shell. If tests indicate a leak, the exchanger must be partially dismantled to determine its source. To find a leaking tube, the shell is filled with water under pressure. This water will enter the tube at the point of the leak and then run out the tube end. By watching the tube sheet, you can often tell exactly which tube is leaking. These procedures will help ensure proper operations and warn of problems before the situation gets out of hand. In this program, you've been introduced to two methods of transferring heat: conduction and convection. You've seen that heat exchangers can meet the plant's needs efficiently depending on their design for both heating and cooling purposes. You've also seen the importance of regular maintenance. For the final review, open your workbooks to Period 3. Thanks for watching.